Hello everyone, and thanks for watching Edupedia World video. This is the second video in the unit of current electricity, and in this video we'll be studying about resistors. We derived Ohm's law last time, which is a law you've probably seen before, and it says that V is equal to IR, or basically across any resistor. A resistor is anything that has resistance. Now for us, whenever we talk about resistors and whenever we put them across a battery in a circuit, these straight parts are assumed to be conductors or conducting wires which have absolutely zero resistance. If the resistance is zero, then even if there's a current flowing through them, the potential difference will be zero. That's why we can say that if this point has potential 0, then this has potential 0, this has potential 0, this has potential 0. And if this has potential V, then this has potential V, and this has potential V. These two do not need to be same, because across them, if there is a current flowing, then V is equal to IR. In fact, I will be V by R. V minus 0 divided by R. But if we apply the same equation here, then R will be 0 and so V will be 0. So V1 minus V2 will be 0, or rather these both potentials will be the same. If this was V1 and this was V2, then I would have been V1 minus V2 by R. Right. So let's start with the standard concept of resistances, which you've already seen in capacitances and in heat transfer, which is the concept of series and parallel. Now I'm not going to spend a lot of time on that because you've already seen that with resistors in previous classes, 9th or 10th, and in 11th class you've already seen that with capacitors and in heat transfer with rods. So I'll just do the same thing here. Let's talk about series first. Now V is equal to IR. What happens in series? In series, I is the same and V adds up. So for example, let's say this has a potential 0, this has a potential 0, this has a potential V. That means the EMF of the battery is V. This has a potential V. Let's call this V1 and V2. Right. So if a current I is flowing through this side, remember we've talked about Kirchhoff's current and voltage law previously. We'll talk about them again in this chapter in one of the next videos. But right now all we need to know is that if I is flowing through this end, it is coming out of this end, because the current flowing in has to equal the current coming out. I goes through here, I goes through here. So the current across each of these three resistors is I. Let's say the resistances are R1, R2 and R3. So the three equations using Ohm's law we'll get are V minus V1 is equal to IR1, V1 minus V2 is equal to IR2, and V2 or V2 minus 0 is equal to IR3. Now what is the definition of equivalent resistance? It will be V divided by I. If across a system of resistances I apply a battery of potential V and it draws in a current from the positive end of magnitude I, then V by I is called the equivalent resistance, because this is the same current it would draw if the resistance system was replaced by a single resistance of magnitude R. So you add these three, these two will cancel, these two will cancel, you'll get V is equal to I times R1 plus R2 plus R3, or the standard result for series, R equilibrium. So why am I saying R equilibrium? R net is equal to R1 plus R2 plus R3, right? Dot 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 if there are more of them, right? R equivalent here. Okay, so now what happens in case of parallel connections? In parallel connections, V is same, whereas the current adds up. So R1, R2, R3, all connected across the terminals of a battery. If this is at 0 and this is at V, this is at 0, this is at V, all three are at 0 and all three are at V, and it draws in a current I. That current splits into three: I1, I2, I3. From Kirchhoff's current law, I is equal to I1 plus I2 plus I3, because across this junction the current flowing in is I and flowing out is I1 plus I2 plus I3. right? And we'll apply V is equal to IR across all three of them. The potential difference across all three of them is V. So V is equal to I1 R1, V is equal to I2 R2, V is equal to I3 R3. Now we'll take R1, R2 and R3 to this side, and we'll add these three up, which will give me I. So I is equal to V times 1 by R1 plus 1 by R2 plus 1 by R3, but of course it has to be equal to V by R. From that we get the result which you already know. 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3 and dot 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 if there are more of them, right? So these are the standard cases for series and parallel. Next, let's look at what happens to resistance of a material when we change the temperature. Remember, when we were deriving Ohm's law, at one point we substituted sigma for a complicated quantity which was Ne squared tau by 2m, right? This was conductivity. So resistivity is opposite of that, reciprocal of that, 2m by Ne squared tau. Now what was tau? Tau was the average lifetime between collisions. If this is the way a molecule or electron moves, then the average time between turns, between this and this, this and this, this and this, you take all the time intervals between collisions, you take the average of that, that is tau. As temperature increases, these molecules start moving more rapidly and the electrons also start vibrating more rapidly, and so the average collision time will decrease, right? This is the important. You can actually remember what happens to resistance with temperature, but if you want to understand it, this is where it all comes from. As we increase the temperature, molecules start moving more rapidly and the average time between collisions decreases. So at low temperatures, what might have been a motion like this, at high temperatures will be a motion like this. They should all be straight lines, by the way. Some of them I've by mistake made curve. So the average time will decrease. That means resistivity will increase. So resistivity and hence resistance increases as temperature increases for conductors. For conductors is important because actually if you talk about semiconductors, which lie between conductors and insulators, it's the opposite. As temperature increases, resistivity decreases. But we're not talking about semiconductors right now. We're talking about pure conductors. And for pure conductors, this is the rule that follows. In fact, we follow a rule similar to what we used in heat transfer. We will generally say rho is equal to rho naught times 1 plus alpha T minus T naught. This is the same equation we saw for heat, not for heat transfer, for thermal expansion, that the length was 1 plus alpha delta T, right? In this case, alpha is called temperature coefficient of resistivity, right? Now, as the temperature changes, the resistivity will change, but the length and area also might change of the resistance. But what actually happens is, I kept repeating this in heat transfer, in thermal expansion, that when you heat an object, the amount by which its length increases is generally very, very small. But the amount by which a resistance might change with temperature is actually somewhat significant. So the change in length and area can actually be ignored when you're talking about change in resistance, because length and area will change by a very small amount. So generally the equation which we end up using is R is equal to R naught times 1 plus alpha T minus T naught. Strictly it should be R, instead of R it should be rho L by A, instead of R naught it should be rho naught L naught by A naught. But we are assuming that L naught is equal to L and A naught is equal to L, because compared to the change in resistance or resistivity, the change in length or area is actually quite small. There's one more topic left in resistances, and unfortunately this is a topic which you will have to remember. There is no other way around it, and it is the color code for resistors. In board exams and CBSE, you'll probably have to remember the table, but for entrance examinations like IITJ, you don't have to remember the table. Technically this is in the syllabus, but they don't expect you to remember the values for each and every color. What happens is, when you get resistances in a lab, they look something like this. right? So you can bend these two ends and you can attach them to a breadboard or attach them to any circuit. And resistances usually have 3 or 4 different colored bands, and those bands generally tell us what the resistance is. So first I'm going to write a table, and for people for whom this is in the syllabus, unfortunately you will have to remember the table, there's no other way around it. The colors are black. Oh, excuse me, I don't know why I limited myself to this. The colors are black, brown, red, orange, green, blue, violet, grey, white, gold and silver. So if you take a random resistance from a lab, these might be 4 different colored bands. It might be blue, brown, green, silver, something like that. And when we're talking about, what we'll talk about is 3 things: numerical value, multiplier, and tolerance. Numerical value is decided by the first 2, multiplier is the third one, tolerance is the fourth one. Right, so I'll just write N, M and T here in the table, right? So the numerical values here are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 being white, right? Then the multipliers are 1, 10, 10 to the power 2, 10 to the power 3, dot dot dot, till 10 to the power 9. 10 to the power 7, 10 to the power 6, 10 to the power 5, 10 to the power 4. Right, so white has 10 to the power 9 as the multiplier. Then gold and silver we go in the opposite direction, 0.1 or 10 to the power minus 1 and 0.01. I'll explain all this in a minute, but I'll have to draw the table to explain it. You'll find the table if you Google it anywhere. And the tolerance is only for gold and silver, and it's 5% or 10%. Right. Now let me tell you what these mean by taking just a simple example. Let's say the colors for a resistor are brown, yellow, green and gold. So brown and yellow are numerical. The first 2 are the numerical values. So brown has a value of 1 and yellow has a value of 4. So the numerical value will be 14. Right. Then you have the multiplier, which is the third one, in this case green. Green is 5, right? So 14 into 10 to the power 5. Sorry, the multiplier is not 5, it's 10 to the power 5, right? If green was in the numerical value, we would use 5, but the third one is green, so 14 into 10 to the power 5. This is basically the resistance. So 14 or 1.4 into 10 to the power 6 or 1.4 mega ohm. This is the resistance of this wire. You just need the first 3. The fourth one actually tells you the tolerance, which is another way of saying the error. Right. So if the fourth one is gold, that means we have an error of 5%. So 1.4 mega ohm plus minus 5% of that. So which, if you went to calculate, would come out to be 1.4 plus minus 0.07 mega ohm. Right. If the last one is silver, then you have an error of 10%. And if there is no last one, that means sometimes you'll just have 3 bands. That means the tolerance is 20%. That means least certain. Right. So I hope one example should make this clear to you. I'll just take another random example. Let's say you have red as the first, yellow as the second, blue as the third, gold as the fourth. So red and yellow would be 24, blue would be 10 to the power 6. So 24 into 10 to the power 6, and gold would be 5%. Plus minus 5% of that. This would be the resistance. Right. So this is how you can unfortunately this table you'll have to remember. I just suggest that 0 to 9 and 1 to 10 to the power 9 and minus 1 minus 2 you can remember easily once you remember this sequence. So just try to create a mnemonic or an acronym to remember this sequence. Right. So this completes resistors. In the next video, we look at batteries and how batteries are influenced by resistances in them or resistances outside them. Thank you.